All right, here we go with a complex problem from the circuit part of this unit. We have a circuit that has both a series and a parallel component. I've hooked up my battery to this portion here, which is parallel. We know it's parallel because the current has to split off, and it has to either go, and here's my first current, it either has to go to the top portion or it has to go to the bottom portion. So let's call this I1, and then I2 is down here. Then it meets back up, and we have this original current that makes its way through R3 back to the battery. All three of these resistors are light bulbs, and I am trying to think about which of these light bulbs would be the brightest, which would have the largest amount of current flowing through them, given this circuit. So since this is complex, I know that I have to take this and reduce it to equivalent resistance. I need to first do it for this parallel portion, so parallel portion. And then once I do that, I'm going to have an equivalent resistor here in series with this resistor. So then I'll have to do it for the series portion. Then finally, I will work backwards to solve for the current going through each resistor. Work backwards to solve for current through each resistor. Let's think about how this works. First, I want to remind you guys of our equations to find equivalent resistance with a series and with a parallel circuit. So the first portion I said, let's look at the parallel portion and let's reduce that to an equivalent resistor. So our circuit should look something like this, where this is still going to be my 4 amp R3, but now over here I'm going to call this REQ1, my first equivalent resistance. I've taken these two and I combined them into one. To solve for that, I need to use my parallel equation, that 1 REQ1, because that's what I'm calling it, equals 1 over, well, what is R1? R1 is 4 ohms, R2 is 6 ohms. 1 over 4 plus 1 over 6. So when I do that, I put this into my calculator and I get that REQ, 1 over REQ, is equal to 0.417. The next move that I would do in my calculator is that I would raise this number to the -1. Because if I do that to both sides, I'll flip this equation so that I can get REQ1 is equal to 2.4 ohms. 2.4 ohms. So now I just figured out this resistance. So now I have a series circuit, remember this is still 9 volts, and I can now reduce this to an equivalent resistance. And this is what the final equivalent resistance would look like. There's my resistor, and this would be REQ2. To find this, I would need to pull out my series equation for equivalent resistance. REQ2 is equal to, well, we just add up our resistors. 2.4 ohms plus 4 ohms gives me 6.4 ohms. And this is still 9 volts. All right, this is great. Now I have one battery, one resistor. I could use Ohm's law in order to solve for the current running through this reduced circuit. Let's do that. My I is V over R. My V is 9. My REQ, that's 6.4. 9 volts over ohms. What do I get when I do that? I get 1.4 amps. So the total amount of current that's flowing through here is 1.4 amps. I'm going to create a chart so that I could map out exactly how much current is going through each resistor, thinking back to my original circuit. So this is what I'll do. I'll say VIR, and I want to put every single resistor into this table, starting with R1, which is 4 ohms. R2 is 6 ohms. And R3 is 4 ohms. But that's not it, because I started to reduce things like REQ1. I need to put that in my table as well. REQ1, which is 2.4 ohms. And then I reduced this to an equivalent resistance of 6.4 ohms, so I'm going to put that in there as well. REQ2, 6.4 ohms. And what I mean when I'm working backwards to solve for the current, I want to start with my equivalent resistance and then work until I can say I know the current here running through I1 and I know the current here running through I2. What I do know is that this equivalent resistance is working with 9 volts. So if I'm filling out parts of my table, I could put 9 volts here. Notice that these three variables are variables of Ohm's law. V equals IR, or I equals V over R, depending on how you like to see it. So I could solve for my I, which I just did, and I got 1.4 amps. Now we need a bit of conceptual understanding. This came from a series circuit here. What do I know about series circuits? Is the current the same, or is the voltage the same across resistors? It's the current. It's the current. So the current here, this I, should be the same as this I, as the same as that I. So my current that I found going through this resistor should be the same as the current going through REQ1 and R3, which is 1.4 amps. Well, now I have I and R, so I could figure out the voltage difference across these two voltages. And both of them should add up to 9 volts, because I know in a series circuit that part of the voltage goes to one resistor, part of the voltage goes to the other, so that all of the voltage is accounted for. So when I do that into Ohm's law, I times R, and then I times R over here, I get 5.6 volts and 3.36 volts. Back to conceptual understanding. I need to think about what's the same in this equivalent resistor as I work backwards to these two resistors. Is it the current or is it voltage that's the same in parallel circuits? It's the voltage. So the voltage that I found acting on this resistor would be the same voltage difference across both of these resistors. So here's my voltage across REQ1, so it must be the same voltage across R1 and R2. So 3.36 volts is acting across R1 and R2. And now I have B and R, I could solve for the current. Plug that into your calculator and you get 0.84 amps and 0.56 amps. So which one of these, R1, R2, R3, would receive the largest current? Could we pick that out? I1 is receiving 0.8, I2 is receiving 0.56, and R3 is receiving 1.4. So R3 should be the brightest. And that makes sense conceptually because all of the current that was split off has to join back up over here, making this bulb the brightest. But what about of these two? Which one would be brighter? Well, current goes through the path of least resistance. I would expect, before even doing any calculations, that R1 would receive a larger current. Is that what we see? R1 receives 0.84, R2 gets 0.56, so this would be brighter than R2. And this one would be least bright. So that's how we work through a circuit problem, reducing it to something that is simple, and then working backwards so that we could solve for the current or the voltage drop across any resistor. Okay, that's it.